Today's problem asks you to build a data structure that can store key-value pairs and let you retrieve, update, or delete them quickly. Imagine you have a phone book where you can look up a name and get a number, change the number, or remove the entry entirely. How would you design that from scratch? Take a moment. What would you do? The input is a sequence of method calls: put, get, and remove. Each put gives a key and a value. Each get gives a key and expects the associated value or -1 if the key is absent, and each remove deletes a key if it exists. The output is the list of results from every get call. For example, the sample runs put 1 1, put 2 2, get 1, get 3, put 2 1, get 2, remove 2, get 2. The expected outputs are null for puts and removes, then 1, -1, 1, -1. The constraints say there can be up to 10,000 operations. Keys and values are non-negative integers, and the hash map must handle all of them efficiently. This is non-trivial because a naive list would require scanning every entry for each get or remove, leading to slow performance as the data grows. We need a way to jump straight to the right spot without looking at everything. The obvious thing to try is keeping a simple list of key-value pairs. When we put, we walk through the list from the start. If we find the key, we replace its value. Otherwise, we append a new pair at the end. Forget, we again scan the list from the beginning until we either find the key and return its value or reach the end and return -1. Remove works similarly. Scan, find the key, and delete that pair. Let's walk through the example with this approach. Initially, the list is empty. Put 1 1, list becomes 1 1. Put 2 2, list becomes 1 1 2 2. Get 1. We check first pair, key matches, return 1. Get 3. We check 1 1, no match. Check 2 2, no match. End of list, return -1. Put 2 1. We scan. First pair key 1 not match. Second pair key 2 matches. So we update that pair to 2 1. List now 1 1 2 1. Get 2. Scan. First pair key 1 no. Second pair key 2 yes. Return 1. Remove 2. Scan. Find second pair. Delete it. List becomes 1 1. Get 2. Scan. Only 1 1. Present. No match. Return -1. Every operation in the worst case touches every element in the list. So within entries, each put, get, or remove takes big O of n time. The space used is just the list itself, big O of n. This works for tiny data, but becomes painfully slow as n grows. The key insight is to use an array of buckets and a hash function that maps each key to a specific bucket index, so we only search inside a tiny bucket instead of the whole collection. Think of it like a library with numbered shelves. The hash function tells you exactly which shelf a book belongs to, and you only look on that shelf. We choose a fixed bucket count, for example 2069, a prime number to spread keys evenly. The hash function is simply key modulo bucket count. In the constructor, we create an array of that many empty lists. Each list is a bucket. When we put a key-value pair, we compute the index, grab that bucket's list, then scan that small list for the key. If found, we update the value. If not, we append the new pair to that bucket's list. Get does the same. Compute index, scan that bucket's list, return value if found, else -1. Remove computes index, scans the bucket, and if the key exists, we delete that pair from the bucket's list. Because the hash function spreads keys uniformly, each bucket holds only a few entries on average, making all operations run in constant time on average. The array of buckets gives us O, bucket count, extra space, which is constant, plus the stored entries big O of n, so overall space is big O of n. You'll spot this pattern when a problem asks for fast key-value lookup, insertion, and deletion all together, and when the number of operations is large enough that a linear scan would be too slow. Those two signals, need for constant time dictionary operations and high operation count, point straight to a hash map with bucket hashing. Time complexity is big O of 1, constant time on average for put, get, and remove, with a worst case of big O of n if all keys collide into the same bucket. Space complexity is big O of n for the stored entries, plus a constant-sized bucket array. Try the next problem, same pattern. Subscribe for more step-by-step algorithm breakdowns.